Welcome to The Explainer. Today, we're diving into the story of a secret code that was so simple it only used basic addition, yet it was thought to be unbreakable. It was praised as a revolution, right before it got spectacularly broken. It's a story about pure genius, a single fatal flaw, and a legacy that, believe it or not, helps protect us all today. So think about this for a second. Imagine a digital lock so tough that every computer on Earth working together couldn't crack it for billions of years. But what if the secret to building that lock, and the key to opening it, was based on something you learned in first grade? Just adding up a few numbers. Well, back in the 1970s, a couple of cryptographers asked that very question. And what they came up with was one of the most brilliant and most famously flawed codes in history. So to really get why their invention was such a big deal, we first need to understand the fundamental problem they were trying to solve. This was a challenge that had been frustrating spies and governments for centuries. Okay, so before the late 70s, pretty much all cryptography was symmetric. Think of it like a password for a shared file. You've got one single key, one password that both locks and unlocks the information. Simple, right? But it creates this massive problem. How do I get that secret key to you securely in the first place? I can't just text it to you because anyone could be listening in. This headache is known as the key distribution problem. And the solution to that problem was this absolutely revolutionary idea: public key cryptography. The whole concept is to create a kind of mathematical trapdoor. It's a puzzle that's super easy for anyone to set up using a public key, but it's practically impossible to solve unless you have a secret piece of information. And that secret, your private key, is what lets you instantly solve the puzzle and read the message. Which brings us to the knapsack's clever trick. In 1978, Ralph Merkle and Martin Hellman came along and proposed a system that seemed to do this perfectly. It was elegant, it was simple, it only used addition, and it was way faster than its famous rival RSA. Their whole system was built on a classic computer science puzzle called the subset sum problem. Now, the idea is simple. I give you a big list of numbers and a target number. Can you find a handful of numbers from my list that add up perfectly to that target? Sounds easy, right? Well, it's not. For a random list of just 100 numbers, this problem is what we call NP-complete, which basically means even our fastest supercomputers would just give up. But here's the genius of it. What if the numbers in that list weren't random at all? This is the secret sauce. This is the trap door they built that turns an impossibly hard puzzle into something a kid could solve. Merkle and Hellman used a special kind of list called a super increasing sequence. The rule is simple. Every number has to be bigger than all the previous numbers added together. And when you have a list like this, solving the puzzle is a piece of cake. Let's say our target is 34. You just work backwards from the biggest number. Does 31 fit? Yep. What's left? 3. Then you just go down the list. Does 15 fit? Nope. 7? Nope. 3? Yes. And you're done. It's instant. So this easy sequence is the secret. It's the private key. But of course, you can't just publish this, or everyone would be able to solve your messages. The real question is, how do you hide this simple, elegant structure in plain sight? You do it with a bit of mathematical magic called modular arithmetic. You take each number in your easy private key, multiply it by one secret number, and then divide it by another secret number. But here's the trick. You only keep the remainder. This process completely jumbles the sequence and turns it into chaos. And you can really see that transformation here. Look at that private key on top. It's orderly, predictable, super increasing. After the disguise, it becomes the public key on the bottom, a chaotic-looking list of numbers with no obvious pattern. It looks just like one of those impossibly hard problems we were talking about. So the system was set. A sender uses the hard public key to encrypt a message. Then, the recipient uses their secret numbers to reverse the disguise, which turns the hard problem back into that easy one they can solve instantly. It seemed absolutely perfect. But it wasn't perfect, not even close. In 1982, a cryptographer named Adi Shamir, who, by the way, was one of the inventors of the rival RSA system, took a closer look and found that the mathematical disguise wasn't nearly as good as everyone thought it was. So here was the fatal flaw. The math used to jumble the numbers was what's called a linear transformation. Think of it like this. If you have a drawing on a rubber sheet, you can stretch it and distort it, but the basic relationships between the points don't change. That's what was happening here. The disguise left behind a subtle mathematical echo, a geometric ghost of the original easy-to-solve pattern, still hiding inside the public key. Shamir had this brilliant insight. He realized if there's a geometric ghost, maybe you can find it with a geometric tool. And as luck would have it, a brand new algorithm had just been invented that was the perfect tool to go ghost hunting. That tool was the Lenstra-Lavaz algorithm, or LLL. Now, you don't need to understand the deep math here, just the basic idea. Imagine a vast, multi-dimensional grid of points, called a lattice. The LLL algorithm is exceptionally good at finding the shortest possible paths between points in that grid. Shamir realized that the hidden private key created one of these unusually short paths. All he had to do was use LLL to find it. The result was devastating. The supposedly unbreakable code, which was designed to be secure for millennia, could now be cracked by the LLL algorithm on a 1980s computer in under an hour. Let that sink in. The trapdoor had been found and the entire system was broken. So the Merkle-Hellman crypto system was dead. But the story doesn't end there. In a beautiful twist of irony, its failure led directly to one of the most important developments in modern cybersecurity. You really can't make this stuff up. The very mathematics of lattices and the LLL algorithm, which were used to kill this early system, became the key to building something far, far stronger. This timeline shows the incredible journey. In '78, the knapsack system is invented. Just 4 years later, LLL breaks it. But fast forward to today, and that same lattice mathematics now forms the backbone of systems designed to protect our data from the threat of quantum computers. The Codebreakers tool became the Codemaker's foundation. This whole saga taught the world of cryptography two incredibly important lessons. First, just because a problem is hard in general doesn't mean every version of it is secure. You can accidentally build in a shortcut. And second, you have to be extremely wary of linear transformations. They often hide secrets very, very poorly. Which leaves us with this one last thought. The story of Merkle-Hellman is a powerful reminder that in the constant cat-and-mouse game of cryptography, today's brilliant, unbreakable solution can all too easily become tomorrow's cautionary tale. It just makes you wonder, what ghosts might be hiding in the systems we all rely on today?